This is EE533 Network Process Design and Programming Lab 9 report. So Lab 9 is about network process integration and refinements. We are part of Team 3. Team 3 members are Akshaya Rajakumar, Siddarth, Sadeesh Kumar, and Shreyas Jaikumar. So for Lab 9, we had to do the integration of all the CPU, GPU from both teams and main network process fiber for that. So this is the main structural design for that we have implemented. And yeah, just going on to the circuit. So this is an actual Verilog code for the network processor. This is for the integration of network processor with our CPU and GPU. So we have used our CPU for this. I'll show you the CPU code here just down. So this is the main CPU code we have used, which was all ARM architecture commands. And we have made some modifications in this, like we took an IMEM outside the remote IMEM and kept it as like an IMEM so that we can push the data into the IMEM. If we kept like inputs for all the IMEM parameters to push it in and got like out from one port. So basically dual port right now with one read port and one write port. So we made modifications for that in our CPU to give instructions and went out for processing all network elements. And also we are done, as we're using our main FIFO memory, we are just removed our data map and we are just getting the input and output values from that directly. So yeah, so these are like correct. We removed our deep data map and like getting input and outputs for our like the signals we required for that data map. That's the modifications for our CPU. For GPU, the modifications are similar modifications have been done. Here, yeah, it's having a yeah over here. Like, similar modifications we done where we removed our data memory for our GPU, and also we have had a small change for move immediate with able to getting 64 values for which is kind of useful for processing data network packages and to load the data like packages into the GPU and also for loading uh, for tensor core operations. Over to Akshaya who will explain changes.
Okay. So here we have the pipeline of the CPU here, GPU here. And here for the execution stage, here we have a mask rig here to incorporate the thread ID. So what happens here exactly is when there is a compare instruction that say example compare thread ID with 3. So that gets compared and the mask rig gets set. So that the next operation, so that lane alone is operated when the next operation is being executed. So yeah, so that's it. That is what I have written here. By default, all of the lanes are like operational, and if there is a move immediate enabled, I mean move immediate instruction. So then the mask becomes the lane, like the mask is encoded in the instruction, and the lane which gets the immediate value is enabled. And if it's a compare instruction in the processing element, that is the next stage, then the mask register gets updated according to the compare instruction output. And also we have the pipeline here. This is all similar to the CPU as well. All of the registers are pipeline here. And now we have the EX1 stage here where we have the processing element here. And this processing element has like 4 instantiations or like 15-bit processing elements. And yeah, we are like taking it. So basically this has like 2 execution stages for B float multiplication and 2 execution stages for B float addition. So when an FMA is done, the data passes through all of the four stages so that the FMA can be done. And if it's multiplication, it will be done in the first two stages, and if it's addition, it will be done in the last two stages. And then we also have incorporated the ReLU inside the B float. So at the last stage, depending on whether the instruction is ReLU or not, we'll get the output. Yeah, and here we have, this is the last stage. So we have the ReLU. We have the ReLU out here as well. And now the tensor unit will be explained by Siddarth.
Okay. Yeah, so this is how we had made modification for GPU. And now coming over to the main codes. Um, yeah, so from main code, this is convertible V4. So for that, we need to have a control signal to select which is going to have the control, either GPU, CPU, or net FPGA. As you can see in the diagram over here, behind boxes which are control using the select line. So here, this control logic. I'll show you the control logic now. It's a pretty simple logic for select lines. Basically, you build with a basic combination circuit for that. Similarly, for write enable. So if any of them want to write and write enable beyond, so the FIFO map. Similarly, for write condition and read condition of NetFPG, this is actually important for read and write pointer, which I'll be going next into. So for this is a read and write pointer. So for our FIFO, we need to increment and decrement the read and write pointer. This will be the write pointer will be based upon if write condition is on. Similarly, for read pointer will be based upon read condition. We have a code for that, so that not this will notify if it's empty or full. That is, yeah, if we don't want, so the hazard conditions, we don't want that. So yeah, going on to the marks is again scaled up our niche marks is to get all the three values. So it's like a 4-to-1 marks. So for which is for both behind for 8-bit and as well as 72-bit. 72-bit is for our data. The FIFO data, sorry, the NetFPG data will be about 72 bits, around 8 bits are for control logic, and rest 64 is for data, actual data. So we have done an implementation for that. So we got the 74 and 8 bits for our address lines. And yeah, that's the main stuff for our FIFO. Sorry, for the integration the net processor. I'll show you a small test bench code I wrote, wherein I'm sending the data for a control net FPGA as a network processor, but just as a proof check so that. Oh yeah, so we're able to get some data. So this is what I just sent as an external source for input for that FIFO out, and I'm able to get A, B, and C. Will get so. Well, yes. So yeah. So we're using this code, we have just modified our IDS code and then we have moved over to our, we've done synthesis and went to our net FPGA. So I'll stop sharing and I'll ask Akshaya to share the remaining process.
Good evening. My name is Shreyas Jaikumar and I'm part of Team 3. And this is the demo video pertaining to Lab 8. Because of the fact that we heard, from a synthesis point of view pertaining to the GPU, it does create a lot of timing issues and other area related constraints. And that is why, instead of going on a sequential basis, we concurrently decided to come up with two different designs, by altering the ISA to some extent, by varying the number of module files present and etc. A long story short, we just decided to come up with two different designs, and I will be talking about the design that I worked on, and later on in this video my teammates will be talking about the second design pertaining to the GPU data path. So the key differences between the CPU data path and the GPU data path on a broad basis is that for the GPU data path, we have to we made sure that there is Google's brains float BF16 type of BF16 instructions, like as you can see here, BF16 underscore add underscore sub dot v and BF16 underscore mult dot v. This is a key different. This is a key. This is something different compared to the CPU. And apart from that, also the thread ID register, and of course the main part, which is the tensor unit. Now currently, and of course, like based on how the custom ISA that we have defined, how based on the PTX script that we map the thread ID to, and etc., those changes and all are being reflected. Of course, due to time constraints, like I'm not going to go over all the details, but just a summary from a high level point of view. So currently my design from a simulation point of view does support R type of instructions, I type instructions, both conditional and unconditional branch instructions, and also thread ID related instructions. However, the tensor unit instructions, to be honest, are not exactly functioning as it's supposed to, like with the ReLU activation as well, which is why I'm not including that as the list, as part of the list of executables or deliverables. So these are the screenshots which I obtained after having simulated my design in Xilinx ISC 10.1. And as you can see, of course, this is the entire list of instructions that are being fed into the instruction memory. And this is an ensemble of, there is like a multiple type of instructions present over here: R type, I type, branch, vector mult, floating point, FMA instructions, and thread ID related instructions, and etc. So as you can see here, of course, due to time constraints, I cannot trace or go by an instruction basis and say like the register address is matching, the data is being correctly loaded into that. But because of the fact that we demonstrated that in detail for the CPU, and here the logic pertaining to those instructions is pretty much the same, ergo those instructions are all correctly working. And as you can see in the waveform, like for the out data from the data memory is being like exactly what it is, and etc. So yeah, just a quick overview of the just a screenshot pertaining to the first part of the waveform. And then in the second part of the waveform is something which is unique to the GPU data path, is, as you can see in the last, as I'm pointing in the cursor, are the signals pertaining to the thread ID. And I believe there was an instruction which said thread ID X at register 8. And accordingly, because of the fact that the in data for the thread ID is hard coded at 1, as you can see, for register 8, for all the entire 64-bit data is being broken down into 4 lanes, right? So accordingly, it's 1, 1, 1, and 1. So yeah, so that's it. That's it for my part of the video, and from now on, my teammates will continue. Thank you.
Yeah, now we are on the NetFPGA. Yeah, so now we are on the NetFPGA, and I'll just show you the ideas. Yeah, so this is the ideas .v top file. So here we have integrated the main code 5.4 that Siddarth has shown, and I've also added the control signals here. So what we had done is basically we took the pass through for like the fall through small FIFO version, like the pass through version, and then we modified it to like integrate the CPU GPU integration FIFO as well. So here we have like the FIFO input, like the control signals and control net FPGA that is also controlled by the FIFO signals. And also we have the IMM write enable, PC enable, select, which can be controlled using the software registers. So I've defined the software registers here. So here we can see, as you can see here, like we have like 4 software registers and 4 hardware registers. And so basically we can this control is like a 32-bit register, and this is the bits that we'll be using to control the for the functions. So bit 0 maps to IMM write enable, bit 1 is PC enable, bits 3 and 2 are control net FPGA, and bit 4 is select. So yeah, we have done that. And we also have a output register here, like we are pipelining it to incorporate for the BRAM latency. So I'll show you the synthesis folder as well. As you can see here, I've already done my synthesis, and I can maybe show the mapping report. Yeah, I've done the synthesis for the main FIFO here, and this is the resource utilization. So we also have generated the bit file. Now I'll be going to the netFPGA and I'll be loading it. Now I'm in the netFPGA. Now I'll go ahead and show you all of the files that I've written for reading the registers and as well as the loading into the IMEM. Now, so here we have all of the registers defined and their corresponding software and hardware registers. And yeah, this does reg read, reg write, and all regs. And I also have another file which loads the instructions into the memory. So this is like writing the instructions into the like giving it to the FIFO so that it gets loaded in the iMemory. Now I'll go ahead and download the bit file. Yeah, now I've downloaded the bit file into the memory. Now I'll do all regs. So as we can see, initially all of the data is 0. So now I'll be loading the instructions into the IMEM that I'll do with the Perl command. So all of the instructions are being loaded. Now if I do all regs, we can see that the last instruction loaded, last instruction address, the instruction, and you can also see the instruction out of the previous instruction. So now I'll switch on the network and see if the network is working, like the interface is working. So now I'll be doing the control registers, like the control register is responsible for like switching on or off the network mode. So I'm going to write into that register, which is 2002C with a value of 10. And now if I do all regs, you can see that data is we have not enabled the PC now. We just like switched on, but we have not pinged it. So now I'll do RTD add, and then I will ping to one of the nodes. Yeah, as you can see here, the ping is working. Now we'll do all recs and see if there is a data flow in the VRAM. So as we can see here, there is like data inside the VRAM. So this indicates that the network is able to interact with the FIFO module and the VRAM gets updated. Now I'll go ahead and enable the PC. So for that, I'll be doing right 12. So right now the PC is at 0. As you can see, PC outright is 0. Now I'm going to enable the PC. And now let's after the PC gets enabled, the instructions they get executed on inside the processor. So now I'll switch off it like the PC. I'll do all right. So as we can see here, there is like new data into the memote low and memote right. Now I can also go and read the different addresses and find out like what is there in the VRAM. So now I'll read into the first memory position. So yeah, now I'll read it. So the instruction out, oh no, not the instruction out. The yeah, I can do all that. Yeah, as you can see, the address reg is 1. So we are reading into the first location of the memory, and we can see we have like some data, like some different data here, like after the PC has executed. Like the PC is switched on, like after the instructions are executed. Now I'll read to the second location. So we can see here the address is 2 and we have some data here. Now I'll do 3. Yeah, we can see like a different data here. So from this we can infer that the network is able to the network and the GPU CPU interface has been done, and the packets that are sent from the network are able to like reach the VRAM, and that can be shown here like the memo low and high, and also that uh, our design is able to ping onto different nodes and receive and send data packets. Yeah, thank you.